There we go. I got a keyboard. Looks okay. Okay, so we are going to start talking about one of the sections that students don't like. Very interesting. But we're going to talk about a lot of different molecules and the process of cellular respiration. And so as I start going through everything, just take deep breaths and just don't get overwhelmed, okay, as we're going through it. When we get to the point, if we get to the point where I'm going to tell you to start how you learn the cycle, let me rephrase that. It's strictly memorization, right? Memorizing the cycle. I'll give you some hints on how to do that. That make it easier for you. And it's a good mental calisthenics, I guess, for the brain. But we'll worry about that when we get to that point. So this is a chapter that starts, the next two chapters are cellular respiration and photosynthesis. So we're going to start with cellular respiration. So keep in mind, so one of the things that I think is so amazing about cells is that you have all these cells that you are composed of, and if you stop and really think about it, you have about, I can't even remember how many cells there are, but all of those cells are undergoing processes all the time, right? And everything that your cells are doing, which are determined by the things that you as an organism walking around are doing, all of that requires energy. Okay, and so we say that in general, life is a lot of work. And now we're not being philosophical, we're not talking about your career, we're not talking about what you're going to do once you graduate from here. We're talking about what your cells are doing every single day, all the time. Okay, so because life is so much work, you need energy. And the way that you get energy to do all of the work that is required in you as an organism, the way that you get that energy is through cellular respiration. Okay? So remember, we talked about kinetic energy, but we talked about potential energy. And that energy is stored in chemicals molecules. Okay, so basically what we need to do is we need to get that energy out of those chemical molecules and get them in your cells so they can do work. Yeah.
I think the first part of the word is
It sure is. Thank you. Oh yeah, because my line was further than it was before. There we go. Okay, so we're going to keep coming back to this over the next couple of chapters. So we've got photosynthesis and cellular respiration. Okay. Photosynthesis is going to give us organic molecules and oxygen. The organic molecules and the oxygen are going to go into cellular respiration. The result of cellular respiration is we are going to get ATP, and that ATP, we're going to get the release of some heat, and we're going to get cellular work. So that's like all of the work that your cells are doing while you're just sitting there, right? While you're just sitting there, your cells are making lots and lots of different proteins and doing lots of work. And that's coming from the ATP. The power to do that is coming from here. The byproduct of cellular respiration is CO2 and water. And CO2 and water feed into photosynthesis. And of course, we have to put some sunlight out here. That's my sun. It's our light energy. So what we're going to do in this chapter is we're going to focus on this, on cellular respiration. And then what we'll do in the next chapter is focus on photosynthesis. But I want you to keep this entire cycle in mind as we go along. So we are going to spend most of our time talking about aerobic respiration. So air, the first part of this is Greek for air. And of course, this stands for bio, for life. We're talking about the process that is giving living organisms their life through the intake of air. It is the most prevalent and efficient catabolic pathway that we have. Our reactant in the pathway is going to be oxygen or air. And this is a pathway that most prokaryotes and eukaryotes undergo. Now, there are some exceptions. So we do have organisms that can harvest energy without oxygen. An example of this is fermentation. That one of our groups did in lab or in the yeast. Okay, that's the process of fermentation. If we are without oxygen, then we call that anaerobic respiration. The prefix "an" means without. The prefix "a," if you put the "a" in front too, that also means without. So overall, cellular respiration is both anaerobic and aerobic. Okay, but we are primarily going to be we mostly refer to as aerobic respiration. So in general, thinking about the cycle, we're going to take organic compounds and we're going to add some oxygen to that, and we're going to produce CO2 and water and energy. And this is why the process occurs. Now you can use different organic compounds, and we're going to start by focusing on glucose. And this is one of the most common that we see, but after we get everything down for glucose, then we'll talk about how this works for proteins and for lipids. Okay, but we're going to start first with glucose. So glucose, of course, is C6H12O6, and it is the fuel that is used by most cells. Glucose, this molecule has a delta G of minus 686 kilocalories per mole. So if we can break down that glucose, we can get almost 700 kilocalories per mole. Okay, before we can actually start through the processes of a cellular respiration, we have to do a little more in-depth chemistry. We're going to talk about redox reactions. So redox reactions, this is just an abbreviated way of referring to oxidation, reduction reactions. And there's lots of oxidation reduction reactions. It's just that they play a major role in both cellular respiration and photosynthesis. So we're going to talk about them a little bit to get this in our mind to understand what we're going to talk about in more detail later. Redox reactions, what all reactions, these reactions do is they transfer electrons. So we're going to have oxidation and reduction, and these always have to go together. You can't have just a reduction reaction or just an oxidation reaction. You have to have both. And the reason for that is because oxidation is the loss of an electron, and reduction is the gain of an electron. And so if we're going to strip an electron from one molecule, we're going to have to put that electron somewhere. So we're going to put it on another substance. Even though this is a gain of an electron, because electrons have a negative charge, then their charge is reduced, further reduced. Okay, so we can look at a non-organic example. So if we look at sodium chloride and break sodium chloride, we've already talked about the ions that come together to form the ionic bond that forms sodium chloride. This sodium is going to lose an electron, and that's why it has a positive charge. So sodium is oxidized because we have the loss of an electron. Because of that, we end up with a positive charge. And our chlorine is going to gain an electron. So this is reduced. We have the gain of an electron. So we can generalize, we can just generalize this using X's and Y's. So we have a substance with an electron, and we are going to take this electron and we're going to lose this electron. So this is still oxidized. And we're going to now move that electron to our other substance. So Y is reduced. So in this generalized formula, your Xe is your electron donor. Because your Xe is reducing Y, we say it is the reducing agent for Y. Because Y is reduced. And then your Y is going to be your electron acceptor, and it is the oxidizing agent for X. So much of what happens in through multiple stages in the process of cellular respiration, but particularly at the end of cellular respiration, is transfer of electrons. Okay, so we're doing this through multiple protein complexes. So you can have, you can have, so this is the case where we're actually moving those electrons. So, right, we have an ionic bond. There's cations and anions, and we have an ionic bond. You can have redox reactions that don't include a complete transfer, so they end up more like our delta negative and delta positive. So if we take methane, CH4, and I'm just going to write the formula up here first. This is a reaction where we're going to get carbon dioxide plus energy plus water. Okay, so in methane, these hydrogens are covalently bonded, right? So our electrons are covalently bonded. And they are equally shared around that carbon. Okay, so when they're bonded to that carbon, those hydrogen molecules, which contain an electron, are equally shared among that carbon. We're going to take them off of that methane and we're going to move them over here to our carbon dioxide. So we're going to lose those. We're going to lose those. We're going to lose the whole hydrogen. We're going to lose it off of the CH4. So when this happens, we have our oxygens that are here. In this case, remember these are just two oxygens. So our electrons here again are shared equally with each of our oxygens. So those are both shared equally. We're going to take those now and we're going to move these hydrogens down here. We took those hydrogens and we moved them down there. And so now what has happened is we have reduction where we picked up those two electrons. You know, we haven't picked up just the two electrons, right? We've actually picked up the whole hydrogen atoms. But these are now unequally shared. So these are now unequally shared electrons, right? Because they're going to spend more time around that oxygen than what they did when they were over here around that carbon. Okay, so we basically have moved those hydrogens along and we've ended up with our water molecule, right? So this is our oxygen with our hydrogen. And we've ended up, now we've taken and we've made these, this whole thing, we've made the delta negative and the syn delta positive. Whereas before, everything was not charged. So we still have a redox reaction. Okay, without sort of a complete transfer, like we saw over here. We've just ended up making a charged substance from an uncharged substance by moving those electrons. So oxygen, if we look at the electronegativity, right? So the electronegativity is just that bonding that is going to result with oxygen. So this bonding is with oxygen results in unequal sharing. Because of that, oxygen is one of the most potent oxidizing agents that we have. So oxidizing, so this is, the way that I always think of this is like rust. So if you have things like metals, et cetera, you expose them to air, they rust. And that's partly because oxygen is such a strong oxidizing agent. It's really good at accepting those electrons. Okay, so now, with that in mind, let's go back to our cellular respiration formula, where we have our glucose, and we're going to add oxygen again, and from that, that's a 6. From that, we are going to get 6 CO2, 6 water, plus energy. Okay? So we are taking those hydrogens and we're taking them off of here. And so we are losing our electrons here, so this is oxidized. And then our oxygen is being reduced because we see our gain of electrons there. So the thing about those hydrogens, remember a hydrogen is a proton and an electron. So if you have organic molecules with many hydrogens, these are excellent fuels because they contain lots of hydrogens and you can move those hydrogens around. And every time you move those hydrogens around, you can get energy from the process. So not all of them, but most release energy with electron transfer. So like your fossil fuels are hydrocarbons. So they're just strings of carbons with a whole bunch of oxygens on them. And you start stripping off those hydrogens and you get lots of energy from there. Organically, for us, those macromolecules that we talked about that had lots of hydrogens were carbohydrates and fats, those fatty acid tails. These guys have many hydrogens. And because they have many hydrogens, they have many electrons. And so they have a lot of energy. So these guys can play a role in the oxidation of molecules, and we can get lots of energy out of that. So that electron is going to travel with the proton. Okay, which basically means that we're moving a hydrogen atom through this process. So we have substances that are called electron carriers. And so electron carriers, what electron carriers do is they pick up hydrogen atoms or they pick up electrons and they move them to someplace else. So one of the main electron carriers that we're going to talk about through cellular respiration is NADH, or NAD+. And so NAD+ is a coenzyme that's used through the process of cellular respiration and in other processes. The full name for this is nicotinamide adenine dinucleotide. This is a derivative of the vitamin niacin. You've probably heard of niacin before. It's one of your B vitamins. And this is a derivative of that.
Dr. Hildebrand,
Yes.
it's really hard to read the board right now. I don't know if it's the you
Let
can
me-
fix.
How about
Yes, that is
that better?
yes.
Okay, I gotta make sure I
Thank
get.
you.
Well, I have a little bit more cord. One thing you have to promise not to laugh when I run into you. But I'm pretty sure I will. Okay, let's try that. In which case I need to move my line over a little bit. We're not seeing past here. Okay. Okay, so NAD plus is an electron carrier or an oxidizing agent that we're going to be focused on during cellular respiration. But like I said, it plays a role in other reactions as well. So let's look at methanol. Okay, and then we'll put this electron carrier here. We have an enzyme to lower the activation energy. And that's going to give us methanol or formaldehyde. Plus NADH plus a proton. Okay, so you can see we're stripping off this hydrogen. So this hydrogen consists of one electron and one proton. Okay, we're also stripping off this hydrogen, which consists of one electron and one proton. Okay, so we added an electron and a proton here. So we can just, it doesn't matter which one we take, but we will take this guy and he gets moved over here. So we move the whole atom. Okay, and then remember we were plus over here, so we were short an electron here. So we added our full hydrogen atom here. Okay, so we added an H. And notice I don't have a charge here anymore. Okay, so I removed that charge by adding this electron. Okay, and so what that gave me left over was this proton. That makes sense? So NAD plus is one of the most efficient and most used electron carriers. So this is what we're talking about when we talk about electron carriers. We're talking about those substances that will pick up hydrogen atoms or electrons, and they will move them. They will move them someplace else. Okay, when we talk about photosynthesis, our electron carrier is NADPH. It's got a phosphate group attached to it. Okay, so everybody understands redox reactions, right? You're doing better than me. I know just enough about redox reactions. Don't ask me to do chemistry. I just know enough to understand what I need to know for biology. Okay, so now that we understand that we can move electrons and hydrogens, and we get energy from that process, and we can have those substances move things around in the cells. Now we can start talking about cellular respiration. Okay? So I'm just going to write the formula up here again. I know I'm just reading up about 6 CO2 plus 6 water plus energy. I'm just going to put ATP because we need to start thinking about that energy. Okay? So first, let's look at an overview before we break down each of the stages. So this is a mitochondrion. Okay, I know it looks like one. So that's our mitochondria. And so outside the mitochondria, we're in the cytosol. So we're starting with glucose. So one of the things that differs when we start with a lipid or we start with a protein is you come in at different stages of the process, right? But we're going to start with glucose. So we're going to start in the cytosol. And the process that we begin with is a process called glycolysis. And glycolysis is going to take our glucose, and it is going to give us a molecule called pyruvate. In the process of going from glucose to pyruvate, we are going to get an electron carrier. Okay, and I'll put that in when we get there. Our pyruvate, we're going to move our pyruvate into the mitochondria. And we have a cycle. So anytime we have a cycle, we have starting products, and we have to regenerate those starting products. This cycle is called the citric acid cycle, which I'm going to abbreviate CAC. No, I need to write it there. So that's the citric acid cycle. From that, we are going to get some electron carriers. And then also in the mitochondria, but in a special place in the mitochondria, we have the last stage. And that last stage is oxidative phosphorylation, or an electron transport chain, so ETC, or an electron transport pathway, ETP, sorry. Okay, so we're going to generate an electron carrier from glycolysis. And that electron carrier, it's NADH, is going to feed in at this final stage. We are also going to have 2 electron carriers. We're going to have NADH and FADH2. Those are both electron carriers, and they are going to be our starting molecules for oxidative phosphorylation. In the process of each of these steps, we're going to get some ATP. So we're going to get some ATP from glycolysis. We're going to get some ATP from the citric acid cycle. Okay. We are also going to get some ATP from oxidative phosphorylation. However, the way that we get these is different. So the ATP that we get from our first 2 steps is a product of what we call substrate level phosphorylation. Okay, so remember, phosphorylation is the movement of a phosphate group. Okay, so in substrate level phosphorylation, to get ADP, right, or to get ATP, we have to go from ADP to ATP. And so we have to put in a phosphate. So for substrate level phosphorylation, okay, we need to have a substrate. We need to have a molecule, okay? So you're going to have an enzyme that transfers a phosphate group from a substrate, which is just a molecule, to ADP, okay? So in substrate level phosphorylation, we require a substrate. We require some molecule that has a phosphate group that we can strip it off. For the last production of ATP, this is oxidative phosphorylation. Okay, now for oxidative phosphorylation, no substrate is required. So the ATP that is produced at this stage is not going to require that you have a substrate already sitting there that you're going to take your phosphate off. Because there's no substrate, so because you don't have to make a molecule before you can strip the phosphate off, here is where we're going to get most of our ATP. We'll get ATP in those other stages. But we're going to get most of our ATP in that last stage because we don't need any intermediary. Okay, so remember that glucose, right? So our glucose had negative 686 kilocalories per mole. At the end of this process, we're going to get somewhere between 27 and 32 molecules of ATP. And we'll talk about why it's not a precise amount. We'll talk about that when we get to the end. Okay, so we're going to get that much out of each of those molecules. Remember, your ATP has 7.3 kilocalories per mole. Okay, so let's look at, let's look at glycolysis first. The very first stage. So in general, what's going to happen to glycolysis is we're going to go from that 6-carbon glucose, and we're going to get a 3-carbon product. And because we're taking 6 carbons, so we're going to go from our 6 carbons, we're going to get 2 3-carbons, and those 3 carbons are pyruvate. Okay, so we're going to split our glucose. Now, the thing about glycolysis, this first stage, is that you have 2 components of that process of glycolysis. So with glycolysis, you have an energy investment portion at the beginning, and then you have an energy payoff. Okay, so basically, you have to have ATP to start. You need some ATP to start the process of glycolysis. Okay, so we're going to start with glucose. And the first thing that we're going to do is put some ATP in. Okay, so we're going to put in some ATP, ADP, so I removed the phosphate group. Remember, it's the removal of the phosphate group that gives you the energy. And I'm going to put that phosphate group on that glucose molecule. So I'm going to get glucose 6-phosphate. So I put it on my 6th carbon. The enzyme that does this is hexokinase. Then what I'm going to do is to take that glucose 6-phosphate and I'm going to turn it into fructose 6-phosphate, right? So all I did was change the form to an isomer. Remember, glucose and fructose are isomers of each other. And the enzyme that catalyzed that reaction is phosphoglucoisomerase. Right? So here I just added a phosphate and then I made a new isomer. Then I have to put energy in again. So I'm going to put in some ATP again to get ADP out. So now that tells you that I'm going to add another phosphate onto my molecule. And I'm going to get fructose. I'm going to put it on the first carbon, 1,6, and now we call it bisphosphate. The prefix bi or bis meaning 2. The enzyme that does that is phosphofructokinase. Okay, so I've now at this point I put in 2 ATPs for my reaction. At this point, this is where I'm going to split it. I'm going to cleave it. Okay, I'm going to cleave it into 2 different molecules. One is going to be dihydroxyacetone phosphate. So one of the phosphates went with this. The other molecule is glyceraldehyde 3-phosphate. Remember, my phosphates were on 2 opposite ends, on the first and the 6th carbon, and now what I've done is I've split that 6th carbon. These are 3-carbon molecules. We don't usually call this glyceraldehyde 3-phosphate, we call it G3P. And I want you to take special note of G3P because G3P shows up in photosynthesis. So these 2 that are split, so we have aldolase that is doing this split, and the dihydroxyacetone phosphate, those molecules don't hang out like that for very long. They get converted over to G3Ps. Now they can back convert, but the ratio of conversion is about 2 dihydroxyacetone phosphates to every glyceraldehyde 3-phosphate. So I'll write it this way, about 2 to 1. So most of your dihydroxy phosphate is getting converted right away, the glyceraldehyde 3-phosphate. And it's the glyceraldehyde 3-phosphate that goes forward. Okay, this usually just gets converted over. The enzyme that does that is isomerase. Okay, so we have put in 2 ATP molecules, and this is the end of our energy investment, is putting in those 2 molecules. So it cost us 2 ATPs. to get everything started. Okay, so this glyceraldehyde 3-phosphate, I'm just gonna make an arrow over here, because this is what goes forward. So because the conversion comes across, everything now is 2 D3Ps. Because we're starting with our glucose. So now we've got 2 G3Ps. The conversion to this first stage is going to take this and we're going to convert it to 2, 1, 3 bisphosphoglycerate. Right? So we're going to take 2 ADPs and get 2 ATPs out of this process. Okay, and the enzyme that does that is phosphoglycerol kinase. I got you one ahead, sorry, just a minute. Wait, don't write that down. Erase. I had to skip this. This is where we get our electron carrier. NADP to NADH. From this point, we get our first ATP. And that is phosphoglycerol kinase. Skip a step. This enzyme here that gives us this is triose phosphate dehydrogenase. Okay, so there's our first electron carrier. There is our ATP, our first ATP. We're going to take our, 1, 3, and then this is going to give us our 3 because we stripped off those phosphate groups, phosphoglycerate. Okay, so we took this off the first carbon, we took off that phosphate group, and we put it onto ADP. Our 3-phosphoglycerate is then going to go to 2-phosphoglycerate. And in the process of doing that, we just move the phosphate group from the third carbon to the second carbon. In the process of doing that, we're going to get water. The enzyme that does that is phosphoglycerolmutase. From there, we are going to have 2 phosphopyruvates. And that is going to be endolase. And then finally, we're going to get 2 pyruvates. And we're going to take our phosphate group off of our phosphoenolpyruvate. So we'll have 2 ATPs or ADPs and get 2 ATPs. And the enzyme that does that is going to be pyruvate kinase. Okay, so this is the metabolic pathway for Is this catabolic or anabolic? Which one breaks down, right? Because we're breaking down. We're going from a 6 carbon to a 3 carbon. Catabolic. This is our catabolic pathway. It's going to break everything down. So if we look at overall what happened through the process, okay, so overall, we used 2 ATPs. We gained 4 ATP. Therefore, we had a net gain of 2 ATP. But we also got 2, oh, I should have done that. Sorry, I put a 2 in front of these because we've got 2 molecules. We also got 2 electron carriers. And those electron carriers, like I said, are really important because they're going to go into that last stage. Okay, so remember our glucose has negative 686 kilocalories per mole. Our ATP has 7.3. So 7.3 times 2, 6, 14.6 kilocalories per mole. So of our 686, 14.6 has been converted to ATP. Right, so let me do this real quick. 517. So we still have over 670 kilocalories of energy left from our starting. So that 671 is going to be contained in those 2 pyruvate molecules. We haven't gotten hardly any energy out of this process. What we have done is we have made our precursors for the next step. And we have gotten 2 electron carriers. Remember, these guys go for oxidative phosphorylation, which is where we said we get most of our energy. And these guys are going to go to the citric acid cycle. That is like the best way in the world to end a Friday afternoon lunch. Right? Yeah. Because I know this is going to keep you awake all weekend. You're going to think about this all weekend. Right? Yeah. Okay. There you go. All these steps, of course, are in your book. And what's nice about what's in your book is they also give you the structures. So you can actually look at the structures and see how these things move around, add phosphates, strip off phosphates, things like that. All right, good. We're set.
Today.
Oh, okay.
Yeah.
That's fine.
Okay.
Okay, perfect. All right.